Right? So last time I was just starting to talk about finding the limit of a sequence. We did an example, I think at the very end last time, something like lim of n over n plus 1. So one trick that you can use to do these is to divide through everything by a power of n in order to put n's in denominators everywhere. So in this example, the trick, I think this is probably something you've all seen before. The trick is to divide everything on the top and bottom by n. Another way of saying that is multiply by 1 over n on the top and the bottom. That turns this into a 1 over, and on the bottom you distribute the 1 over n. The n times 1 over n becomes 1, and then 1 times 1 over n becomes 1 over n. And then this, you can take the limit. When n goes to infinity, that 1 over n will become 0. So you get 1 over 1 plus 0, which is 1, right? That's a standard trick. And you can do this for functions also. You've probably all seen this before. Here's a little variation on that, which is a little more interesting maybe. How about this? 3n over the square root n plus 5. What's weird about this, of course, is the square root. And everybody knows you cannot just take square root n plus 5. It's not the same as square root n plus square root 5, right? That's not allowed. So we have to... well, we have to keep the square root together. That's what I'm saying. What can you do, though? Actually, you can do the same kind of thing. So I see a power of n on the top. So I'm going to, again, multiply by 1 over n on the top and the bottom to cancel out the n up top. Oops, sorry. Before the equal sign, can I just say, I am, again, going to multiply 1 over n over 1 over n. All right? So what I get on top is just going to be 3, right? And on the bottom, I guess I get 1 over n times square root n plus 5. And now we are going to shove the 1 over n into the square root. And now it can't just go in there as is, but I hope you've seen something like this before. How it goes in is like that. It sort of has to get squared when you push it inside the square root sign. That's because if you were to actually do the square root here, this 1 over n squared, you would take the square root, and it would become 1 over n, which is what it was before. So when you push something into a square root sign, you've got to square it as it goes in. But anyway, now we can distribute under the square root sign. And it's going to be 3 over, okay, square root here. And then I guess n... So we are distributing here, right? 1 over n squared times n is 1 over n, plus 5 will be 5 over n squared. All right. And now I take the limit. Now that all of my terms involving n's have n's in the bottoms, so those two guys downstairs are going to become zeros, because when the n becomes infinite, I have 1 over n, that becomes like 0, because its denominator is becoming infinite, and also 5 over n squared becomes like 0. So from here, this becomes 3 over square root 0 plus 0, which is, oh, I got a text. Not important. Yes, that's right. I have 3 divided by 0. What is your interpretation of that? Well, the limit does not exist. Actually, this limit is going to infinity, is a more specific thing that you can say, because that's what happens when you have something which is divided by something which is becoming 0. As long as it's positive, you have to be careful about, is it going to plus infinity or minus infinity? Sorry, I got to mute this. Some church ladies texting me. No? All right, I'm sorry, I had to mute. I don't know how to mute just just my texts. So I'm just so popular with the church ladies. I muted my whole computer. If you folks at home want to shout out, maybe hit me up in the chat and I'll see it. Sorry about that. Anyway, yeah, this we can say equals infinity, all right? Because the bottom is going to 0, the top is just a constant. When that happens, it's either going to plus infinity or minus infinity, but this I can tell is plus just because the function I'm talking about here is always positive, right? So it's not going to be negative. Or you could just say dne if you prefer. That's a little less specific, right? Because there are many ways that the limit could fail to exist. That's fine. Okay, so this is a slightly fancier version of that divide by some power of n trick. Any questions about that? I thought about squeezing this in at the end last time, but I didn't want to squeeze it in at the end last time. All right. Actually, both of these examples that we did here, you could also do using L'Hopital's rule. And the first one is pretty easy to do using L'Hopital's rule. The second one is kind of a pain because in the denominator you have that square root thing. But L'Hopital's rule would work for both of these also. All right. Okay, let's just do a few more simple examples. How about, here's a very common example, important, very simple, basic, but important. an equals minus 1 to the power n, all right? This is one in which it is not helpful to think of this just like a function. As we said last time, for instance, I just said for these ones you could use L'Hopital's rule. And what I meant by that is you can imagine that this thing here, it acts the same as this real valued function. This is a continuous function apart from at x equals -1. And then you can use L'Hopital's rule to find the limit of that function, right? This is an example where this cannot be viewed as a continuous function. Cannot be viewed as a continuous function minus 1 to the power x. Why not? I mean, it looks okay, actually, minus 1 to the power x, but that is deceptively simple looking. As a function, f of x equals minus 1 to the power x is not a continuous function. I will say is not a continuous real function. What I mean is, actually, you don't always get real number answers to this. If, for example, we use x equals a half, then we get minus 1 to the power 1/2, which equals square root of -1, which, say what you will about that, it is not a real number, all right? You can say this is an imaginary number, and that's fine, but in any case, we're not talking about, that's kind of outside the realm of calculus at that point. So this is not a real number. So certainly, -1 to the power x is all I'm saying. You cannot consider that to be an ordinary continuous function in the way that we usually would. And so you would not try to turn this into a continuous function and then find its limit by using some trick about limits of functions, or perhaps L'Hopital's rule or something. Cannot work on that because it doesn't make a continuous function. But when you use just ordinary whole numbers n, this is perfectly fine. It works out fine as a sequence. It just doesn't really work as a function. But anyway, what about it then? So what about lim n goes to infinity of minus 1 to the n? Well, this sequence, if you just write out the terms are, when n is 1, you get minus 1, and then when n is 2, you get 1, and then when n is 3, you get minus 1. This just bounces back and forth between 1 and -1. What do you think about the limit of that sequence? Does this sequence approach a specific value when you go, keep on following these numbers out to the right forever? Does it get close to a particular value? The answer is no, it does not. It just goes back and forth between 1 and -1. It never stabilizes on a particular number. So this The limit does not exist, all right? These don't converge to anything. So the lim n goes to infinity. I wrote it m. N is my variable. Limit as n goes to infinity, minus 1 to the n, does not exist. All right? Another way of saying that is minus 1 to the n diverges, right? That was a little bit of vocabulary. Sometimes it's helpful. Now, this example is pretty simple, I think. Sometimes it's helpful to sort of graph the terms of the sequence or plot the terms of the sequence. We can plot them to try and visualize them. Now, I mean, this is a very simple example, but the way you would plot the terms of a sequence, it'd be like plotting a function, only I'm not going to draw a curve here. I'm just going to draw a bunch of individual points. When n equals 1, so it's kind of like, this is like the n-axis. When n equals 1, the value of this sequence is minus 1. Maybe I'll put big red dots. All right, when n equals 2, the value is plus 1. So the next one is up here. Then the next one is down here and up here, etc. And you can see as we go out to the right, those dots do not stabilize on any particular value. They don't approach anything because just some of them are 1 and some of them are minus 1. They don't get close to anything else. All right? It is often going to be, helpful to try and think about pictures like this, a plot of a sequence. Okay, great. Let's talk about, here's a slightly more interesting example. How about an equals minus 1 to the n divided by n? So the terms of that one, the first one for n equals 1 would be negative 1, followed by, for n equals 2, I would get 1 over 2. For n equals 3, I would get minus 1 over 3. For n equals 4, I get 1 over 4. Then minus 1 over 5, etc. So you're getting basically all the fractions, 1 over whatever, but the signs will flip back and forth, positive to negative. What do you think? Does this one have a limit? Looks like you got to ask yourself, as I look at these numbers here, going out to the right, do they actually get close to any particular number, or do they just bounce around? I think actually they do get close to 0, don't they? They are approaching it from different sides, but that does not matter. So it is true, nevertheless, that these numbers, as you go down the list here, they get closer and closer to 0, right? Because their denominators are becoming basically infinite. Whether it's positive or negative, they are approaching 0. So if you were to look, I'm going to say, first of all, it looks like this. Well, an is 0. If you were to sort of plot these, I will try to plot them in the same way. What they look like is the first one is down here, negative 1, and then I have positive 1/2, maybe there, then negative 1/3, positive 1/4, negative 1/5, positive 1/6, like that, right? And we can see on the picture, if you believe my picture, as you go off to the right, these things definitely do get closer and closer to 0, which means that the limit, well, it looks like the limit of an equals 0. Now, how could you actually demonstrate that? How can we show that this equals 0? I mean, I would like to somehow be able to do this by looking at the formula and doing some kind of algebra tricks or something. This one's a little trickier, though, than the other. So how to show that a lim n goes to infinity minus 1 to the n over n equals 0. The tricks that we used before about dividing through by power of n or something doesn't really work in this case. And you cannot, for instance, change it into a function and then use L'Hopital's rule. You can't change it into a function because, for the same reason as before, you can't make this minus 1 to the n into a function minus 1 to the x because that's not a real function. How can we show that this equals 0? The problem really is in that thing up in the numerator. And there's another trick for doing this. This trick actually only works when you want to show the limit of something equals 0, specifically 0. But here's the trick. A sequence, this is a theorem in the book. Maybe I'll write it as a theorem, but we're not. It's kind of obvious. Like we're not going to talk about doing a proof of this. But anyway, the theorem says that the limit as n goes to infinity of an equals 0 if and only if lim as n goes to infinity of absolute value an equals 0. If some sequence is getting closer and closer to 0, automatically that means that the absolute values of that are getting closer and closer to 0. That's because the absolute value of 0 is the same as 0. Right? So if something is becoming 0, it doesn't matter if it's positive or negative. It's becoming 0. What this means is sometimes you can show that something, that the limit is 0 by instead showing that the limit of the absolute values are 0. So what it means as a trick, it means to show that lim n goes to infinity an equals 0. We can instead show that the limit of the absolute value is 0. Now, ordinarily this isn't really very helpful, but in this particular case it will be helpful because when I look at this thing here, instead of showing this thing is 0, I can show that the absolute value is 0. But the absolute value will just destroy this part, right? That's what makes this part difficult, is because this minus 1 to the n. But if you take the absolute value of that, then that's going to go away because this is either just a plus 1 or a minus 1. Inside of absolute value, it's always going to be a plus 1. All right, so for our sake, I'm going to do lim n goes to infinity of absolute value minus 1 to the n over n, right? And then we can simplify the absolute value. Of course, the absolute value of a fraction is the same as the absolute value on top divided by the absolute value on the bottom. That is a legal trick for absolute value signs. So this is the same as absolute value minus 1 to the n divided by absolute value of n. And the whole point of doing it this way is that the absolute value negative 1 to the n is 1, right? So the numerator of this fraction is always 1. That's because that number inside the absolute values is either plus 1 or minus 1. And in either case, absolute value of that is 1. So I got 1 up top. And then on the bottom, we have absolute value of n. Can we simplify that at all? I can turn my sound back on. Those ladies quieted down. Can we simplify the bottom? Absolute value of n? I mean, what could you, maybe, could you do that? Same as 1 over n? Yeah, what if n is negative?
Then it wouldn't be the same as absolute value.
That's true. Anybody have thought about what if n is negative? Yeah, this is a sequence we're talking about, right? So the n starts at 1, and then it's 2, and then it's 3, right? So you got to get a little used to the fact that, right now, and basically for the rest of the class, we're talking about sequences. This n is always going to be positive. And so you don't have to worry about, well, what if n is negative? As a function, definitely, if this were a function, you would not be able to just replace absolute value n with n. But here, you can. So this step down here is because n is positive.
You said that sequence always begins at 1. What if it begins at 0?
Yeah, so sometimes we write a sequence beginning at 0. But this particular example here, you're not allowed to start at 0 because then you'd have a 0 in the denominator. But in any case, the n will always be positive or perhaps 0. But in this example, the n must start with 1. Just, you can tell by looking at the formula that you're not allowed to use n equals 0 here. All right, so n is positive. I was just going to write in here, since it's a sequence, right? We are not talking about a function. We're talking about a sequence. Okay, anyway, what is lim n goes to infinity 1 over n? That's just 0, all right? And so we showed that the absolute value goes to 0 in the limit, which means the original sequence goes to 0. So I'll just conclude by saying, since lim n goes to infinity, absolute value minus 1 to the n over n equals 0, we know that the limit without the absolute value is 0. Right. So this is the this trick using the absolute values. You can only use it for something which is becoming 0, but this is often what you have to do to deal with the weird minus sign, in particular the alternating signs business. This trick comes in handy for such examples. All right. I want to talk about one more limit rule or limit trick or something like that. Like last time we talked about several tricks about you can, if you have two different sequences, you can add them up and the limit of the sum is the same as the two limits added together. There's one more rule that I suppose could have gone on that list, but it's a bit more, a bit fancier. So this is another limit rule. And this is also something that we have been doing a few times already. I just never brought our attention to it. Here it is. Another limit rule. We can evaluate a limit inside a continuous function. And I'll tell you what I mean by that. So first of all, the rule, just to write the rule abstractly, sorry, that says inside a continuous function. It says this: if I have lim n goes to infinity of f of a n, so if somehow you have part of the sequence is inside of a function, and that is a continuous function, this is the same as f of lim n goes to infinity a n. All right, you can evaluate a limit inside of a continuous function. So again, this is something that I actually did this once already today, and I don't know if anybody noticed, but maybe I will refresh our memory and bring our attention to it. We had something like, this is the second thing I said today with the square root. We turned that thing into, I believe it was a 3 on the top, and then on the bottom it was square root 1 over n plus 1 over n squared. I don't know if the numbers were exactly that, but remember this one, right? 5 or something? I can look that. It doesn't matter at all. N plus 5, so it was, yeah, 5 in the second one. All right. What? Oh, I did the paint bucket instead of the eraser. All right. It's fine. We have undos. Okay, there is a 5 here. Whatever. That doesn't matter. But anyway, if you want to be real technical, ask yourself, how exactly, so the next thing I said, remember I said this was 3 over square root 0 plus 0, right? That was the step, and everybody believed me. But really, behind the scenes, sort of under the hood, what I was doing was, first of all, I did the limit in the numerator and the limit in the denominator, right? So I did lim n goes to infinity of 3, and also the limit in the denominator. This was one of those rules that was in the big list last time. The limit of a quotient is the same as doing the limit on top and the limit on the bottom. So the limit of 3 on the top is 3. And then what did I do on the bottom? Instead of doing the limit on the outside of the square root, I took the limit under the square root. So technically what I did in the next step was this. right? And then I turned those both into, so actually there was yet another step. I broke this up into two different limits, the limit of 1 over n, and then plus the limit of 5 over n squared, and then those were each 0, right? Still inside the square root. But anyway, the important step that I want to draw our attention to is right here, this one, where I push the lim into the square root in order to evaluate the limits. Nobody argued? Are you allowed to do that? Yes, you're allowed to do that. That's what this rule at the very top there says. All right, you're only allowed if it's a continuous function, but the square root is a continuous function, so it's fine. All right, you can push the lim inside of a function, of a continuous function. So technically, it doesn't have to be always continuous. The square root is, you can't put negative numbers in there, but as long as it's continuous among the numbers where you're looking, which it is in this case. Did you have a question? Oh. Yeah, sure. Yeah, I got the allergies too. All right, here's another simple example. How about lim n goes to infinity of cosine of 1 over n? Cosine of 1 over n. So the way you want to think about this is, as the n is very big, that thing on the inside is going to look like 1 divided by some huge number. So the thing on the inside is basically going to look like 0. And then I take the cosine of 0, and I get 1. So the answer to this limit is 1. But really, the way you would write this out in steps is, I push the limit through the cosine, like that. This is the first step. And then the rest of it is simple now. So ignoring the cosine for the time being, we do the limit inside the parentheses, and we get 0, because 1 over n goes to 0 when n goes to infinity. And so this ends up just being cosine of 0. And then the cosine of 0 actually equals 1. So this is a simple case where you want to do that rule. You push the lim through the cosine. And this is legal as long as that function is continuous. All right. Any thoughts about that one? Great. Okay, so this is about it for these kinds of rules and tricks for evaluating limits. I hope it doesn't sound like just a bunch of random facts at this point. Let's talk about I want to talk about one more sort of very important class of examples. An important example sequence. This actually has a name. It's called the geometric sequence sometimes. Geometric sequence. This is just a sequence that you get by doing powers of a particular number. So, for example, something like 2, maybe just to be explicit about it, I'll say 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, etc. That's one example, or you can do this with any number you like, right? So you could also do something like, so these, if you wrote those terms, they would be 2, 4, 8, 16, right? But you could choose different numbers there. So you could do also 3, 9, 27. These are the powers of 3, right? Or you could do even something like, this is kind of silly, but the powers of 1, right? Those are the powers of 1. They're all 1. Or something like the powers of -1. Actually, the powers of -1 gives you that sequence that we talked about before, right? -1, 1, -1, 1. Or you could even do the powers of, say, a fraction. 1/2, then you get 1/4, then you get 1/8, then you get 1/16, all right? All of these are examples of a sequence that you get by just taking powers of the same number over and over again, all right? So in each case, we have a to the n equals some specific number to the n, and in our book they use r for this number. So I'll just say where r is some specific number. It can be any number, right? Positive or negative. All right. So what I want to talk about for the next few moments is when does this converge, if ever? Really, and you know, you can do this for different values of r. So what I want to talk about is for which r does it converge? And for which r does it diverge? So maybe we could just, like, let's just look at those ones that I wrote already. How about the first one here? 2, 4, 8, 16. What do you say? Converges or diverges? Diverges. Yeah, this one, those numbers, they just keep on getting bigger forever. So that one diverges. Yeah. Yeah, so this one converges. These values, remember what it means to converge is as you go down the list, the numbers get closer and closer to some specific value, which in this case it converges, and we can say actually to 1, right? Converges to 1. Do any of the other ones converge? Actually, this one also diverges, right? For the same reason. But we can just talk about it individually. How about the one that's going -1, 1, -1, 1? That diverges. We just talked about that one a few minutes ago. This also diverges. Although it diverges kind of in a different way, like these two, these both, you could say diverges to infinity for those, right? Because the values, they get bigger forever. Whereas that one, -1, 1, -1, 1, that diverges, but it doesn't go to infinity. It just goes back and forth. How about the last one there? Does that converge or diverge? You got to ask yourself, these numbers as you go down the list here, are they getting closer and closer to any particular value, or? Yeah, I think the last one also converges to 0 this time, because those fractions, they are getting closer and closer to 0. So this one here converges to 0, right? So there are, I suppose, several options, right? Some of them diverge, some of them converge, some converge to 1, some converge to 0. Well, let's talk about it. I mean, there is actually a rule about that's very simple once you know the rule. When you look at R, can you tell me if it converges or diverges? All right, that's what I want to talk about. So I think one easy thing that you can say is if the R is greater than 1, if the R is greater than 1, then if you think about what this sequence looks like, then we have things like, you know, it's always going to be r squared, r cubed, r to the 4. But if the r is bigger than 1, then these numbers, they just get bigger every time, right? Every time you do a higher power of a number that's bigger than 1, you get just a bigger answer. This increases exponentially. In fact, this looks like the function, something like the function a to the power x, right? Where if a is a number that's greater than 1, then that function a to the power x looks like this. And this goes to infinity. This happens if the r is greater than 1. So we have this thing. This, I'll just say, increases without bound. Every time you take a higher power of this number, it just gets bigger every time. And so that is going to diverge. So if r is greater than 1, then Lim N goes to infinity r to the n. actually equals infinity, right? You can say it does not exist. You can say it diverges, but more specifically, the limit is infinity because those numbers will get bigger forever. All right. I think that's a simple case that everybody can agree with. What about, here's another simple case, if r is between 0 and 1. So I'll write it this way, 0 less than r less than 1. In that case, you're talking about a fraction, right? Maybe like a half or a third, a tenth, whatever. In that case, actually, I think it's going to look kind of like this, right? If it's a half, it's going to go to 0. Also, if it's a third, it's going to go to 0, right? In fact, anything less than 1, if you take powers of that, it's going to get a little bit smaller every time. Even if it's like 0.9, 0.9 times 0.9 is 0.81, right? So it gets a little bit smaller every time. And these will go to 0. So if r is between 0 and 1, then Lim N goes to infinity, r to the n equals 0, right? We're talking about fractions multiplying by themselves over and over again. And they get smaller every time. They will go to 0. If you want to think of that as a continuous function, it would look like this. This is the graph of a to the x when a is, when a is between 0 and 1. Right? They look like that.
And if r is 1, it's just
Yeah, what about if r equals 1? I left out that case. I said if r is greater than 1, the limit is infinity. If it's less than 1 but greater than 0, then the limit is 0. What about if r equal 1? What do you think? Yeah, then this is like one special case, right? Then it looks like, I'll just say then an equals r to the n looks like 1, 1, 1, right? So this converges to 1. So that's like a very special situation, right? There's only one possible outcome here. So I'm going to say, so lim 1 to the n equals 1, right? All right. Is that all the possibilities? Actually, there's more possibilities. We have so far talked about if r is bigger than 1, if r is between 0 and 1, or if r equals 1. What else could we talk about here? If r equals 0, yeah, what would you say in that case? Yeah, then it's going to be 0 to the power n. What would that look like as a sequence? Yeah, they're just all zeros, right? 0 to the 1, 0 to the 2, those are all equal to 0. So actually, this is similar to that sort of case that I just said a moment ago. No. So in all of these examples, I'm starting n equal 1. Although it doesn't matter, except in this case, if you start with n equals 0, you get 0 to the power 0, which actually there's some debate about what 0 to the 0 is. It kind of depends who you ask. Well, there are two kind of conflicting laws of math at play, because 0 to any power is always 0, but it's also true that any number to the power 0 is always 1. So you have to kind of pick which rule wins in this scenario, and there isn't really a standard answer. So I don't know what your calculator would say actually if you do 0 to the power 0. Maybe your calculator will give you an answer, but yeah, you might get an error. The short answer is this is like a cultural decision. In some contexts, it makes sense to say the answer is 0. In some other contexts, it makes sense to say it's 1. In some other contexts, it makes sense to say it does not exist. If you think of it as if they were functions, what do you get? Error. All right. Yep. Yeah, I don't know what Alexa will say. Anyway, I don't want to think about 0 to the 0. That's the conclusion here. So let's start the n at 1. So if r equals 0, then a n is 0 to the power n, which looks like 0, 0, 0, 0, etc. Right? And so the limit in this case equals 0. All right. Is there any other scenario? We talked about greater than 1. Also talked about equal 1. Also talked about between 0 and 1. Also talked about equal 0. I think we can have negatives. Now the n has to be positive, but like if we look here, like actually this right here is an example where the r is negative, right? The r is the number which is being raised to the power. In this case it was -1. So what about negative values of r? We get a whole kind of spectrum of things that we could talk about now for negative values of r, all right? Let's try and talk about sort of the same kind of range here. So we get a special situation. If r is between -1 and 0, then r is negative, but it's a fraction, right? In this case, we're going to get 0 for the limit because you will get, I mean, it's you're taking powers of fractions, which are less than 1. The fact that it's negative will cause the signs to alternate, but it's not going to matter, right? So this is like, something like -1/2, 1/4, -1/8, 1/16. This is what would happen if r equals -1/2, right? But you can still see those are going to 0, right? The signs are alternating, but it doesn't matter because it's becoming 0 anyway. All right. So if so for r in this range, we get lim n goes to infinity of r to the n equals 0, right? The signs of those things are flipping back and forth, but it really doesn't matter as far as the limit goes. The limit equals 0. Okay? What about if r equals -1? That's the next number that we could choose. If r equals -1, then it looks like this we've already talked about. -1, 1, -1, 1, -1, right? And this diverges. Doesn't go to infinity, but it diverges. And then what about if r is negative, but further to the left than -1? What do you think? Like, for example, if r is -2, then what the sequence would look like is -2, and then -2 squared would be +4, and then -2 cubed would be -8. This is what it looks like for a negative number, which is kind of bigger than 1. All right? What do you say about this? Converges? Diverges? Yeah, this one diverges because it does not approach any particular value. And you can't even say this one diverges to infinity or to negative infinity. Actually, it doesn't go to negative infinity because every other of these terms is going to be a huge positive number. And the other ones are huge negative numbers. It doesn't approach anything in particular. So this one diverges. All right? And this is really all of the possible scenarios. I'm going to try and summarize here which ones converge and which ones diverge. So I'm going to write this as a theorem, which kind of has a bunch of steps. A bunch of different cases. But anyway, here's what it says. I'm going to try and do these sort of from biggest to smallest in terms of numbers. So if r is greater than 1, then lim of r to the n equals infinity, right? That was the first case we talked about. If r equals 1, then lim n goes to infinity, r to the n equals 1, right? That's if it's just 1 comma, just 1 every time, you get 1. Okay, what about if r is between 0 and 1? Remember the limit was 0? But also if r is 0, the limit is 0. And also if r is between minus 1 and 0, the limit is 0. So I'm going to combine all of those cases like this, right? For all of these values, the limit was 0. We had discussed those in 3 separate categories, but we got the same answer every time. So the limit is 0 in all of those cases. And then the last case is if r is less than negative 1, then the limit does not exist. It doesn't go to minus infinity, though, because it has a flip-flopping in the sign. All right, this is the theorem about geometric sequences. All right, I would say I would expect you, I suppose, to have this memorized. I mean, it's not all that hard just to think it through, but if the basic upshot of this is if the r is bigger than 1, then this thing goes to infinity. If the r is small, like a fraction, then you get 0. If r equals 1, you happen to get 1. It's kind of interesting to me that it's impossible to get any other limit. Like there is no such sequence r to the power n where the limit equals 2. Like your only chances are 0, 1, or infinity, that's kind of interesting to me. And the 1 basically almost never happens, right? There's only one specific case which can give you the 1 as the answer. All other answers are either 0 or infinity or nothing at all. All right. Let me just point out these ones are the ones which converge, right? And the other ones diverge. So if you see the theorem in the book, they have a theorem that says it converges if and only if r is in the interval. I'll just write it down. R to the n converges if and only if r is like this. Minus 1 less than r less than or equal to 1. In that case, it converges. And for all of those r's, it converges to 0, except when r equals 1, it converges to 1. All right? That's what the theorem says.
What do we say if r equals negative 1?
If r equals negative 1, it diverges. Because, oh yeah, I didn't put that in my list here. I meant to say that. I just put a little less than or equal to. Yeah, thanks. I left it out of the theorem. But if r equals negative 1, then it diverges. Thanks. All right. This is, I mean, we basically know everything there's to know now about this sequence of r to the power n. Any thoughts about that? Great. Okay. Let's talk about a little something else. By the way, we're still in the first section about sequences. This is chapter 11. We're jumping all the way to chapter 11. 11.1 is all about sequences, which includes everything that I've said so far, plus a little bit more. Let's talk about increasing and decreasing sequences. Increasing and decreasing sequences. Everybody knows from Calc 1, you talk about increasing versus decreasing for a function. It's a common thing in the calculus class to, like, I give you a function, you tell me, like, what part of this function is increasing, what part is decreasing. That's a common calculus type question. For a function, typical way to do that is using the derivative. You could talk about a similar idea for a sequence, although you're just going to have to use totally different techniques. We're not going to use the derivative to discuss this or to define this concept of increasing and decreasing sequences. I think actually it's a bit easier to talk about for sequences than it is for functions. Let me just tell you the definition first of all. A sequence, I'll call it AN, is increasing anyone think maybe you can say what the definition should be? I mean, it means basically the number gets bigger every time. Is there a way, a nice way that you could write that using some kind of mathematical language? Yeah. That's a good idea, although that's not quite enough. There are some sequences which are increasing, but they don't go to infinity. Like, well, for instance, this is not exactly. Yeah, or something like this. This one is decreasing. They get smaller every time, but it doesn't go to negative infinity. It actually goes to 0. It goes to something else. Yeah, I think if I understand you correctly. But actually, it's easier to give a definition for increasing without any reference to limits of anything. Not talking about limits, but the basic idea is the thing gets bigger every time. Can we write that in a simple way? And folks back home can chime in too. I turned my sound back on. Those ladies calm down. Any thoughts? It gets bigger every time. Ask Kroger. What do you think, Kroger? He's not saying anything.
I'm actually unsure, Professor.
Thank you for responding. I appreciate it. He's not sure. That's fine. And nobody's sure. Increasing means it gets bigger every time. Like if I were to write the individual terms, don't write this because we can say it's simpler than this. What about A1 versus A2? If it's increasing, it means A2 is bigger, right? So as an inequality, I could write that. Now, if I say it gets bigger every time, it means this. They all go like this, right? It just gets bigger every time. Now, you could write this as the definition, although that's kind of a pain to write all of that. You can just say this in general when AN is less than AN plus 1, right? That means each one is less than the one that comes after it. That's what Mr. Kroger was about to say, right? Yeah. Thank you. I called him out.
Yep, I was just about to say that,
yes,
actually.
he was just about to say that. Great. I knew it. Yes. Okay, so this is what the definition of increasing. When you see that, I don't know if this is immediately meaningful, but what it means is that each one is, I guess you could say, smaller than the next, right? Right? That means that the next one is bigger. This is one of my favorite things, by the way, when I hear people say things like this in the wrong way. Like, you want to say, like a bunch of people, all my students in my class, it's like, each one is nicer than the one before, right? Sometimes people say that to mean that they're all so nice. But sometimes I like when they say it wrong. They say, each one is nicer than the next. That actually means they're getting less nice for each one you talk to. Yeah. I heard someone say once, oh yeah, I met two guys there, and just one of them was nicer than the other one. They were trying to say like they were both really nice, but it made me think, which one was the nice one? One of them was nicer than the other one. All right. Anyway, each one is smaller than the next. Okay, that's what increasing means. It gets bigger every time. Decreasing is just the same, but the other direction. So a sequence is decreasing. when an is greater than an plus 1. This can be a little confusing, I suppose. You got to make sure the inequality sign is going the right way, but an is bigger than the one that comes after it. Or if you prefer, you could write it the other way around, right? You could say an plus 1 is bigger than an. The next one is bigger than the previous one, all right? However you want to write these. This is what it means for a sequence to be increasing or decreasing. Now, many sequences are not either. It's not like any sequence is either increasing or decreasing, because many sequences, the numbers like go back and forth. We've seen that already. So some are neither. When it's either increasing or decreasing, there's a word for that. So if an is increasing or decreasing, we say, this is a fancier sounding word, we say an is monotone. Monotone. The word monotone, like you've probably heard this like in music maybe, it kind of means something which is staying the same all the time. So the way, in a mathematical context, we use the word monotone to indicate usually something which is changing, but always changing in the same way, or changing in the same direction, or something like that. So a sequence is monotone. It means either it's always getting bigger, or always getting smaller. That is, either increasing or decreasing. Monotone? Yeah. If you just like steady, right? That's a more positive way of calling somebody monotone. All right? Okay, let's just look at some examples. How about if I give you a sequence, can you tell me if it's increasing or decreasing? And can you show why it is increasing or decreasing? How about this? 3n over n plus 1. Is that increasing or decreasing? Now, you can try to just get a feel for it by writing down a few terms, which is a decent idea. Is it increasing or decreasing, or neither? Did I spell that wrong? N-E-I? Yeah, I spelled it wrong. Or neither. Like I said, if you don't know, to get a feel for it, you could try to just write a few terms. So it would look like, if I use, let's say I'm starting with n equals 1 here, although I suppose I wasn't too specific. If I write the terms, starting n equals 1, it would be 3 over 1 plus 1. The next one would be 3 times 2 over 2 plus 1, and then 3 times 3 over 3 plus 1. 3 times 4 over 4 plus 1. These as fractions, this is 3 halves. This one is 6 over 3, which equals 2. This one is 9 over 4, which is, I guess, a little bit more than 2. It seems like these are increasing, right? The first one is 1.5. 9/4 is 2 and a fourth, right? 2.25. This is 12 over 5, which is whatever that is. It's a little bit more than 2 also. 2.4, I think. This is 10 plus 2/5. Should be 2.4. So I'm going to say it seems increasing, but for our purposes, that's not really good enough. I don't want you to just tell me what it seems to be. I want to try to actually demonstrate that it is increasing. Although you have to, before you try to prove it, you have to sort of have in your mind whether you think this is increasing or decreasing. You don't want to try and prove the wrong way. It won't work. So first, just sort of play around with it and figure out, is it increasing or decreasing? It seems to be increasing. Can we demonstrate it? So to show it's increasing, we must show that an is less than an plus 1, right? That's the definition of increasing. Can we demonstrate that? Well, we can plug in to the sequence. Remember, this is an, right? An equals 3n over n plus 1. So what we need, I'm going to plug that in. So we need 3n over n plus 1 to be less than, and I'm going to plug in a sub n plus 1. That means I go up here and I read this, but I replace the n's with n plus 1, right? This is it's just like plugging into a function. an is that. an plus 1 means this, but you use n plus 1 everywhere instead of n. So it looks like 3 times n plus 1 divided by n plus 1 plus 1. All right, that's what I get when I plug in a n plus 1. We need this inequality to be true. And so it becomes our job to demonstrate that that inequality is true. Is it true or not? That's what we have to decide. So I'm going to just try and simplify as much as we can, rewriting this thing over and over again. Hopefully it will become so simple that it becomes obvious if it's true or false. All right? So simplify. Any suggestions? How can I simplify this? Well, one thing is you can, like on the right side, distribute the 3 there, and then maybe add up the denominator. So it says 3n over n plus 1 less than 3n plus 3 over n plus 2, right? I distribute the 3 on top, and I just add things up. The parentheses on the bottom, they're not relevant. You can add it together. This is the same as... Anybody have an idea? How can we simplify this? Or, I mean, rewrite it in some way, perhaps? Yeah, you could divide both sides by 3. All right. You got to remember the first rule of Fight Club is if you multiply or divide both sides by a negative number, you must change the direction of the inequality sign. But I divided by 3, so no big deal.
What did you say next to it?
I said this says the same as, meaning this inequality is the same as this one, right? I want to make sure you keep on rewriting it, something which is equivalent to what you had before. Any thoughts about this? I would say your general approach should be, when you're working with inequalities, is just try and do whatever you would have done with a normal equal sign and sort of worry later about, is this really going to work with inequality? So for instance, you could ask yourself, like, what would you do if you have something like this? How would you simplify? Yeah, multiply across. So you would turn this into AD equals BC. That's what I'm going to do here, although you should ask yourself, is that still legal with an inequality sign? Do I perhaps have to change the direction around? Well, really what this is I multiply both sides by D, and I also multiply both sides by B at the same time, right? That's what the cross multiply thing really means. Are you allowed to do that on an inequality? Yeah, you're allowed to multiply both sides. In this case, I multiply both sides by n plus 1, and also multiply both sides by n plus 2. Everything's fine. Do I need to change the direction of the inequality? You got to ask yourself, am I multiplying by a negative number? The answer is no, because n is positive, so n plus 2 is positive, and also n plus 1 is positive. So it's going to work out just fine to do the old cross multiply thing. It will look like this. Right? We don't have to change the direction of the inequality because n and also n plus 2 are positive. Now, if it had said something like 1 minus n, that would be negative, and then you would have to change the direction. But it didn't say that, so we're fine. All right. Now, what can we do? Well, let's do the FOIL, I guess. Distribute on the left, n squared plus 2n, and on the right, do the FOIL, n squared plus 2n plus 1. What can we do with that? Okay. Certainly not. Yeah. I'm getting paid for this. I don't make mistakes. No. I appreciate your correcting me from time to time. What can we do next? I'm just trying to continue simplifying and eventually end up with something which is obviously true. That's what I'm looking for.
Plus 1 on the right. Would be 1 divided by.
I would rather not divide by anything. Everything here is being added together. I think we should, instead of dividing n squared, how about just subtract n squared from both sides? Yeah. So if I subtract n squared on both sides, then these just cancel, right? And I can also do the same with the two n's, and these just cancel. So all of this is the same as 0 less than 1. This is true, which means all the other ones are also true. This is the end, right? This is true. So it means all the other things, and in particular, the one we started with, is also true. So all these are true. All these inequalities are true. Oh, come on. And so, really, all we care about is the first one. So an is less than an plus 1, which is what we wanted. All right? Simplify those inequalities until it boils down to something which is obviously true. And then that means everything else in your list of inequalities must have been true. All right? This is...
So you're saying that A1 is less than A1 plus 1, and you have A1 is less than 3, and you just split the values.
So that would have shown the definition of increasing means an is less than an plus 1 for every n. Not just, what you just said was, let's only use n equals 1.
Well, I mean, you can substitute any value in there. You can just show that
No, because then you would have only shown it for those two values that you picked, right? Like, you have to show it in general, no matter what the n is. Like what you just said, you could have chosen anything, it would still work. How do you know it would still work? Actually, you have to write all this. That's what this is demonstrating, that no matter what the n is, this one is always less than this one. This is really the only way to be sure that it works for every value of n. I got one of these for you to try. Another chat. How about show that n over n squared plus 1 is increasing. I'll let you decide for yourself. First of all, tell me, is it increasing or decreasing? And then demonstrate it. Blank creasing. Really, that I could have used the word monotone, right? Monotone means either increasing or decreasing. So maybe write down a few sample values, see if you can tell, is it increasing or decreasing? And then once you figure out which is which, see if you can show it. So we only got 5 minutes left. I'm going to write up here. It's possible to write using minus one, but plus one is that's better. Yeah, the opposite, right. The very end of this one will look a little different from the last one we did. All right, let's talk about these just because we've only got a minute left. I know not quite everybody's done, that's fine. Yeah, so it is decreasing. You can just play around with a few numbers and decide it's decreasing. So what we want to show is this. AN is bigger than AN plus 1. You plug into the sequence, you get something like this. I simplify on the right-hand side. This n plus 1 squared becomes this business down here. Do the FOIL right there, and then add the extra one. All right, and then I do the cross multiply thing, noting in the back of my head that these denominators are always going to be positive because the ends are positive. So I don't have to worry about changing the inequality direction. So I get this. Okay, now what? I can continue to, simplify or expand or whatever you want to say. Distribute the n here, n cubed plus 2n squared plus 2n. Greater than, and on the right side, you got to do the FOIL there. It's going to be n cubed plus n squared plus n plus 1. And then we can sort of subtract to simplify things. I can cancel n cubed on both sides. And the rest of this will not fully cancel, but we can subtract n and also subtract n squared. And the left side will say n squared plus n greater than 1, right? Subtract n from both sides and subtract n squared from both sides. And I get n squared plus n greater than 1. And actually, this cannot be simplified anymore, but this is good enough to make our conclusion. Remember, we're trying to boil it down to something which is evidently true. Is it true that n squared plus n is always bigger than 1? Yes, it is, because n itself is a positive number, right? N is bigger than 1. And so what I see on the left side is at least 2, right? So this is bigger than 1. So sometimes in these examples, you have to explain why is this true. Like in our previous example, we ended up with just 0 less than 1, which is, you know, you don't have to say anything to justify that. But here, I'll just say this is true since n is greater than or equal to 1. And so what that means is n squared plus n is at least going to be 2, right? And so definitely it is greater than 1. And so that means that all those inequalities were true. So in particular, the first one, an is bigger than an plus 1, that was our goal all along. All right. I think that'll do it for today. We'll try some more like this next time. We do have homework due as usual. Yes, I'll put it up sometime soon. Maybe right now.